Greetings everyone. Today we're going to be talking about interactions and potential energy. Here we have a tennis ball and a racket. Let's just assume that the racket is not moving, or that we're in the reference frame of the racket. And this tennis ball is moving towards the racket with some speed. After some time, the two collide, and the tennis ball is not moving in relation to the racket. So where did all this kinetic energy go? Well, it went into stretching the racket. So we're going to be talking about how does that have to do with potential energy and the interactions that are going on here. Interactions can either be attractive or repulsive. In the case of the tennis racket and the ball, that was a repulsive interaction, as is many the case of collisions, except when they're totally inelastic and something causes them to stick together. But there are other kinds of interactions that we have in nature. But one thing that we can say in general is that these interactions cause a change in momentum. So we could say that there's some interaction here between the footprints, between the feet of the gecko and the glass that he's climbing on. We can say that there's some interaction that causes the DNA base pairs to bind to each other. We can say that there's some interaction that causes one car, when it collides with another car, for them to be pushed apart. In all these cases, there's some momentum that is being changed. In the standard model of physics, there's four fundamental interactions. There's the strong force, the weak force, electromagnetic, and gravitational. The strong force is a force that binds neutrons, protons together. And it is extremely short range, and it is very strong. That's why we call it the strong force. We're not going to talk very much about that next semester, and none at all this semester, so disregard this. The weak interaction we're also not really going to talk about, but it's another an important interaction that is responsible for basically how the sun works and fusion and fission. Next semester we'll talk in detail about this electromagnetic force, like we talked about with the gecko, how it climbs up glass, how there's hydrogen bonding in DNA, and other kinds of electromagnetic interactions. Another kind of force is gravitational force, and this is really important on the scale of Earth's solar system and galaxies. So weak interaction is also very short range. Electromagnetic is, moderately short range. It's not going to matter very much in the case of how a book may interact with another book unless we're sliding these two across from friction. If they're not touching each other, then there's no electromagnetic forces there. Gravitational forces are very long range. But the thing is that they're also very weak. You may say, but what about black holes? But that's also because of how much stuff is involved. So when we say strong and weak, we mean basically how much stuff is interacting with how much other stuff and how strong is that interaction. So the strong force takes very little amount of stuff to give us a very strong interaction, whereas gravity, we need a very large amount of stuff in order to give us a strong interaction. But it is very long range. So you can say, well, what is friction? And I kind of gave that away a little bit talking about electromagnetic forces. But friction is a force that we commonly talk about. We may talk about normal forces. But basically both of these fall under this electromagnetic types of forces. Basically, this is how electrons and their orbitals of atoms are interacting with other electrons. So in the case of the tennis ball and the racket, before we had some kinetic energy, and then after we had basically no kinetic energy, and something went into stretching the strings. Let's talk a little bit about, let's say maybe there's a big mountain, a river's coming off the side of this, and then we build some dam here. And so we're building up a lot of water. We can use that, this stored energy of the water up high, and turn it into electricity through a hydroelectric dam. Now, instead of water, let's think about this boulder. If we push this boulder off this cliff, it's going to roll down, and it'll roll faster and faster. So somehow, down here, it has some kinetic energy. After it falls, that's going to be greater than zero. But right now, since it's not moving, its kinetic energy is zero. So somehow, being up high lets you store energy. Just like stretching these strings let you store energy in the stretch of the strings, and then that can be converted back into kinetic energy. So how is kinetic energy, which is 1/2 mv squared, how is this related to our potential energy, which we're going to write as U? So let's think about the boulder that's rolling down the cliff. So here we have some mountain. We're going to put a big boulder up here, and the boulder is going to travel down with some speed. So we have x is going to be v initial t plus 1/2 a t squared. But in this case, we don't have t per se, but what we can do is to say that your acceleration is going to be like your change in velocity and change in time. And so what we then can do is look at delta t is going to be the change in velocity over our acceleration. So let's just plug that in. So here we have x is going to be v initial, and then here's our delta v over a plus 1/2 a delta v over a squared. So what then we're going to do is multiply all this out and group some terms together. So we're going to get 2 v initial, v final minus v initial, plus v squared minus 2 v initial, v final plus v initial squared, and all this is over this 2g. We can go ahead and plug in a equals g. And so what we'll find out is that this actually simplifies a great deal to v squared minus v initial squared over 2g. Now you don't need to bother with how this is derived, but this is the really crucial result is, let's just multiply this g over to this side. And so what we're going to get is g delta x, this is how far he travels, is going to be 1/2 v final squared minus v initial squared. So this looks a lot like this kinetic energy. Here we have a v squared. All we're missing is this m. So let's stick that into both sides. So here we have mg delta x is going to be 1/2 m v final squared minus v initial squared. So what this is actually k final minus k initial. So this is our gravitational potential energy, and sometimes you'll see it as mgh. So this is our change in height, basically, is related to how our kinetic energy changes. So as we go down the mountain, we're gaining kinetic energy. And we gain it in such a way that it's linearly dependent on how far down we go, this h. So another important point is that this h can be positive or negative. So here u can be negative, it can be greater than 0, it can be 0. It's really going to depend on where we set this u equals 0 line, or this x equals 0 line. And then wherever we go, if we go up, we get positive potential energy. If we go down below that, we get negative potential energy. But another important idea is that kinetic energy can never be less than 0. It can be equal to 0, that's fine, like the boulder sitting up there, its velocity is 0. but it can never be negative because we have this v squared term here. Alright, so here we have a 1900 kilogram car going at 6.32 meters per second in the positive x direction, and it's going to collide with a truck at rest. Alright, so let's just draw this out. So here we have a car moving at v equals 6.32 meters per second, and it's going to collide with the truck. Speed truck is 0. Then something happens, and the collision is totally inelastic, so that means these two guys stick together. The collision takes place over 0.2 seconds, so this delta t is going to be 0.203 seconds. Assume that no brakes are applied during the collision and that the car strikes the rear of the truck. Okay, now we're neglecting friction between the vehicles and the ground, air resistance, everything else. So, what is the x component of the acceleration of the car? So, here I have a velocity and I have a delta t. So what I need to get acceleration is I need to know how this velocity changes. So I've got to do a collision problem. So it tells me I can start with momentum conservation. And so here we have mc vci is going to be mc plus mt v final. And I can solve for this v final, and I'm going to get 2.4 meters per second. Alright, so then my acceleration of the car is going to be dvc over dt. So the car's final velocity is 2.4 meters per second, and the initial is 6.32 meters per second. And divide that all by the 0.2 seconds that the collision occurs over. And so this is going to be 19.3 meters per second squared. Alright, I can do the same thing for the truck. The truck is initially at 0, and then finally at 2.4, so that's going to be 2.4 minus 0 over 0.2. So that's an 11.8 meters per second squared. Important point up here is that this acceleration is actually negative since it was initially going faster, so it's slowing down at this 19.3 meters per second squared, and the truck accelerates. So then, what is the ratio of these accelerations? So AC over AT, 1.63. I could also look at how the masses are related to each other. Let's look at the mass of the truck over the mass of the car, since the truck is more massive. This also gives me 1.63. So what this tells me is that mass of the truck over mass of the car is equal to minus acceleration of the car over acceleration of the truck. So I could rewrite this as mass of the truck, acceleration of the truck is equal to minus mass of the car, acceleration of the car. If I then think about force is MA, what I get is that force on the truck from the car is equal to minus the force of the car on the truck. So these two, whatever happens during this collision, causing these accelerations, is some force that is equal and opposite. Here we have a 0.3 kilogram cart and a 0.17 kilogram cart are held together by some compressed spring between them. So let's have MA and MB held together by some spring. Now, after a while, we release them, and this 0.30 kilogram cart moves off to the right. So B moves off with 1.1 meters per second. So that means A has to move back this way at some VA. So MB is 0.30. We have conservation momentum we can use. So let's go ahead and employ that. Initially nothing is moving, and then we have MA VA plus MB VB, and then I can rearrange this to be VA equals VB MB over MA. So when I plug this in, I'm going to get VA, it's going to be minus 1.94 meters per second. So A is moving to the left, B is moving to the right. Initially, though, I had nothing moving, and so my kinetic energy initially was 0. After I release these two, I have some kinetic energy. That's 1/2 MA VA squared plus 1/2 MB VB squared. I just add up all my kinetic energies, and I'm going to get 0.50 joules. So this tells me that before the collision, before I released these two, nothing was moving, my kinetic energy was 0. After I release them, I have 1/2 joule of energy. So where does that energy come from? Because I know that energy has to be conserved. So initially, I have the springs compressed. So that's U spring, potential energy of the spring, plus kinetic energy initial, plus what other energy terms I might have. It's going to be the potential energy of the spring final, plus kinetic final, plus, I don't know, maybe I have gravity final too. But in this case, gravity isn't playing a role. There's only left and right, no up and down. My spring is acting after whatever I'm caring about. My initial kinetic energy is 0. So I really just have U of the spring is equal to my kinetic energy final, because energy has to be conserved. So whatever made these objects move had to be some form of stored energy. So I know that my energy in my spring was 1/2 joule.